Hi, I'm Honghu, a second-year doctoral candidate in the College of Civil Engineering in Hunan University. And this is our project, Automatic Tiny Crack Inspection on Bridge Surfaces using Attention-Based Encoder-decoder Architecture. And this project was directed by my advisor, Professor Deng, and Professor Wang. In this project, we try to improve the performance of the existing crack segmentation model to identify tiny cracks. First, let me briefly introduce the background and the motivation of this work. As is known to all, cracks may shorten the service life of bridges and may even lead to severe accidents. And the crack detection is of great significance to maintaining the safety and serviceability of bridges. At present, it is common practice to use bridge inspection trucks or inspection ships to carry seasoned professionals for conducting close-range inspections, which is a high-risk and labor-intensive job. Two representative works were published recently to solve these problems. Deng, etc. created a ring-type climbing robot. The camera was about 25 centimeters from the surface of the bridge pier. Then used the Signet model. The crack with a width of 0.086 mm can be detected. And another equipment was designed by Jen and John. It was a wall-climbing unmanned aero system with the capability of detecting 0.1 mm wide cracks based on the embedded SSD method. And the working distance is about 15 centimeters from the beam. And both of these two studies require that the equipment should be sufficiently close to the bridge surface, because the tiny cracks photographed from a longer distance are often too small to be detected by the existing algorithms. So, we decided to develop a highly sensitive algorithm for the segmentation of tiny cracks, so as to improve the detection efficiency and security. We noticed that the attention mechanism was developed for modeling the dependency between pixels and has been proven beneficial in segmenting cracks. And Wang, etc. proposed a novel convolutional block attention module named CBAM. CBAM combined both spatial attention and channel attention mechanisms. We noticed that the CBAM can be conducted to improve the sensitivity of the network in recognizing tiny foregrounds as shown in the right picture. So, with the aforementioned inspiration got from the CBAM, we decided to embed this useful attention mechanism into the encoder-decoder architecture to improve its performance in segmenting tiny cracks. Here, an encoder-decoder architecture with the feature fusion and attention mechanisms was developed to solve problems encountered in tiny crack segmentation on bridge surfaces. Firstly, a novel ResNet-based network architecture was proposed for extracting crack features. Then, a multi-scale feature fusion operation was introduced to the head of network to enhance the edge details of tiny cracks. Additionally, the architecture has a dual attention module to help separate cracks from the background. Finally, a joint learning loss of the cross entropy and similarity was developed to improve the pool convergence caused by the severe class imbalance of tiny crack images. With the deployment of the proposed method, the UAV will be allowed to detect the tiny cracks on the surface of the bridge at a longer distance, which improves the detection efficiency while enhancing the safety of the flight process. Here is a brief introduction to the implementation process of the attention mechanism used in this article. And for the spatial attention, the average and maximum pooling process are applied in the channel direction, and the output results of the two pooling operations are combined together. The combined feature vector is then applied to a 7x7 convolutional layer. Then the sigmoid function is utilized to generate the spatial attention weight coefficients. Then, for the channel attention modules, it can be seen in the right figure that feature F begins with two pooling operations, including maxima and average pooling, and that two resulting feature vectors with a size of 1 by 1 by n are then input into a shared multi-layer perception to further capture the channel feature. To build the final channel attention feature map, the output feature vectors are combined element-wise and activated using the sigmoid function. And the visualization results of the channel attention vector and spatial attention map are shown in figure below. The 2D spatial attention map in figure shows that the spatial attention successfully guides the proposed network to put larger weights on tiny cracks, and the vectors indicates that the proposed channel attention mechanism generally tends to choose larger weights to act on tiny crack feature maps. To prove the effectiveness of the proposed method, experiments were carried out. Two open-source correct dataset, Correctree 200 and CFD, were selected to evaluate the efficiency of the proposed method. To facilitate apples-to-apples comparisons, the present study replicated all assessment networks using the PyTorch framework, and these listed evaluation indicators were used to quantify the model performance. Then, comprehensive ablation experiments for each component were conducted. To begin, the dual attention mechanism's efficiency was assessed using a baseline model, and an appropriate embedding placement for dual attention mechanisms was determined. To maximize its effectiveness, there were two challenges arise while attempting to integrate the two modules into the network. The first challenge is determining how to combine the two attention modules, and the second one is determining where to place the two merged attention modules. For the first problem, it was discovered in the previous study that sequentially arranging the channel attention module in front of the spatial attention module produced the best result. The second issue is really connected to the network architecture design, which were discussed in this ablation study. The dual attention module was considered for embedding in 4 possible positions, including after feature 0, feature 1, feature 2, or feature 3 in the upsampling decoder. As seen in the table 1, that embedding the dual attention module deeper can enhance the segmentation performance of the model. This is because low-resolution features that contain more semantic information frequently have a bigger receptive field, and the attention mechanism can acquire more context information by capturing global information. The performance of the ResNet series-based model is then compared to that of the model improved by the dual attention mechanism. And a combined learning loss of cross-entropy and similarity is proposed to alleviate the pro-convergence caused by the class imbalance of micro-correct images. As shown in Table 2, the suggested dual attention mechanism has a noticeable influence on network performance, increasing it by an average of 3.07% for the MIOU. Besides, the performance of the SE ResNet 50 with the dual attention mechanism outperforms others, which may be due to the fact that the ResNet 50 and the dual attention module achieved the optimal solution simultaneously. The SE ResNet 50 with dual attention mechanism were used in the subsequent study, and the performance of the correct detection network will be greatly impacted by the imbalanced problem of the tiny correct images. To address this issue, a joint learning loss of the cross-entropy and similarity was proposed, as expressed in the equation. As shown in Table 3, the parameter alpha has a significant effect on the results, and the best result is obtained when the value of alpha is set at around 0.3. Each component and the parameter of the proposed method have been optimized through the ablation study. To further demonstrate the proposed method's effectiveness, 4 typical deep learning-based models, including the FCN, SIGNet, DeepLab v3, and UNet, were selected for comparison based on the CFD and Correctree 200 datasets. The table contains the comparative results, while figure below display a variety segmentation instance. According to the table, the proposed architecture had the highest MIOU. As seen in the figure below, the proposed method predicted outcomes had fewer incorrect and missed detections than the other 4 approaches. The results demonstrate that by including a variety of contextual information, the proposed architecture can mitigate the influence of noise on the identification of tiny corrects, and some supplementary work was added with the UAV field test. The proposed architecture aims at tiny correct segmentation on the surfaces of the bridge. The entire architecture includes a ResNet-based encoder, a decoder with merging context information from corresponding layers of the encoder, and a fusion architecture with supervised learning weights and dual attentions. In addition, a joint learning loss of the cross entropy and similarity is integrated into the network to handle the issue of the imbalanced class distribution. The performance of the proposed model was compared with 4 typical segmentation models. The following conclusions can be drawn based on the obtained results. In summary, the benefits of improving the detection accuracy of tiny corrects are twofold in engineering practice. First, for the same UAV, a further shooting distance and a larger shooting FOV are allowed to improve the efficiency and the safety of the inspection process. Second, allowing the use of a camera with a lower resolution under the same shooting distance reduces the detection costs. And more detailed research content has been published on CAC-IE. Welcome to read, exchange, and discuss. Thank you for listening. Any question, please contact me.